Here we're going to look at Kepler's laws, well, specifically Kepler's first and second laws, because we've already talked a bit about Kepler's third law. There are some important and interesting consequences here, but nothing that is kind of fundamental to what you need to do for this course. So you could think of this as maybe an enrichment video. Specifically, we'll look at conservation laws to help us understand this, the conservation of angular momentum. We've already talked about Kepler's third law that says that for two objects orbiting the same central mass, the ratio of their period squared is equal to the ratio of their orbital radii cubed. This is also true if instead of orbital radii, we're talking about A, which is the semi-major axis. That also works for elliptical orbits. So the first of Kepler's three laws is really just that planets orbit in elliptical orbits, which was a big deal because up to this point, everyone kind of in Western science and thought was looking at circular motion. There was an interesting thing about how circles were maybe more kind of heavenly and godlike and perfect than any other shape. But of course, an ellipse also being a conic section and a circle really just being a special case of an ellipse made for a really elegant solution as well. It turns out the big central mass of whatever you're orbiting in the case of our solar system, the sun, is at one focus. And there's nothing actually at the other focus, but it is a point that we use for, drawing an ellipse. So a couple of words that you'll hear. The semi-major axis is the distance from the center of the ellipse out, or half the longest distance along the ellipse. The semi-minor axis, which is usually given the symbol B, is half of the shortest distance across through the center of the ellipse. Aphelion and perihelion are the words to talk about how close or how far you are, the closest and farthest points from the sun. Helion comes from sun, and peri is about being close, right? Perihelion and aphelion is far away. You may also have heard perigee and apogee. That has to do with the Earth, geological, geo. And so perigee is when you're the closest to the Earth. Apogee is when you're farthest from the Earth, if you're orbiting an ellipse around that. But that's that one. There's also the eccentricity, which has to do with a factor multiplied by the semi-major axis between 0 and 1, which tells us how far the focus is from the center of the ellipse. And for a circle, this is 0 because, the two foci are at the same place. Kepler's second law is that a planet sweeps out equals areas in equal times. And so there's a little animation here, which hopefully will play for us. There we go. Play for me. There we go. The basic premise here in Kepler's second law is that as the object goes around, right, it takes the same amount of time to sweep out the same amount of area. That means that when you're far away from the star, in this case, you are moving more slowly because the area swept out has a much longer arc that's doing the sweeping. And when you're close, you have to move very, very quickly in order to sweep out that same area. So at perihelion, when you are closest, that's actually the point where something is traveling the fastest. Aphelion is where you're going the slowest. So basically, the rate of change of area is constant. The other thing about this is thinking of it in terms of torques and rotations. The sun does not exert any torque on the planets because it's always pulling it directly toward the center. And so it's always pulling kind of perpendicular to the path of motion. And so because of this, we can say that angular momentum is conserved. It's also true that mechanical energy is conserved because we don't have any non-conservative forces, just the force of gravity. And so conservation of angular momentum tells us kind of our justification for why the law of equal areas works, right? We have this little bit of area, right? dA, 1/2 base times height. And if we kind of look at what's happening here, that's 1/2 of r, right? ds is kind of the triangle that we're dealing with there. And especially as this is small, then r is exactly the base of that triangle. We can solve our differential equation, and we need to show that if those are constant, then dA is constant. Well, if the angular velocity or angular momentum is constant, right, then I1 omega 1 equals I2 omega 2. And we're talking about a point particle here, so I is mr squared. And so we end up with r squared omega for 1 and r squared omega for 2 are equal to each other. And that means, oops, clicked ahead too fast, dA is a constant because it's just equal, dA over dt, dA dt is 1/2 r squared omega. So that has to be a constant. An example, at the aphelion and perihelion, v is perpendicular to r. If an elliptical orbit has this eccentricity, what is the perihelion velocity in terms of the aphelion velocity? Well, we start with our conservation of angular momentum. Mr perihelion v perihelion equals Mr aphelion v aphelion. The m's cancel out, and you see that it's just a ratio of the radii, or the orbital distance. And that orbital distance, RA and RP, are really just related to the semi-major axis. Eccentricity has to do with E times A is that distance there, right? If you're halfway there, you end up with 1.5A and 0.5A. So that's it. Just a little bit of a background on Kepler's laws. The interesting one really is that angular momentum is conserved, and that, as a consequence, means that the planets or other orbiting objects behave like they do.